Carl von Richter, who's going to be speaking to you about treating cows badly, a high-fidelity simulator for automated farm provenance. And Carl's our technical lead in the embedded systems and an embedded systems engineer working with CSIRO's Data 61. Take it away, Carl.
So you can hear me and see my slides?
All good.
As I said, as Guy said, I'm a technical lead embedded engineer, so I focus on designing hardware as well as software for small, low-power IoT devices, ranging from asset tracking tags all the way through to sensor networks on farms and large sort of building construction sort of sites. And then as well as that, I do some work. I do a lot of work around how do we get that data from the edge and on those embedded devices all the way through the cloud and store that in data backends. So this talk will be about the simulation of distributed sensor networks. So as Guy said, treating cows badly, this is something that simulation allows us to do. So where this fits within our largest supply chain integrity work is we're focusing this work on farm. So for instance, we're really focusing the simulation work on being able to model on farm devices and how those interact with one another. So for instance, some of the in-field sensor network technologies that we used at the start of the year during our first initial trial, where we utilized some series tags that were attached to animals to do Bluetooth and satellite comms. So these have the capability for Bluetooth and satellite comms, as well as being able to run some embedded logic internally. We also attached other devices such as asset tracking tags. So for instance, we attached this to a water trough, and this was able to identify and self-identify that what it's attached to is this object in the real world. So for instance, so there's context between other devices. Other devices we set up were data relays, for instance. So these data relays were attached to fence posts and stuff like this. This allows us to collect data from the ear tags, plus also asset tracking tags that don't have the long range capability using LoRaWAN. To have that long range capability, so therefore we use these devices to offset that. So Bluetooth is very short range, it's typically only 50 meters, where LoRaWAN you can get several kilometers up to 10, 20 kilometers in in ideal use cases. We were planning to set up, but we were leveraging existing on-farm infrastructure was environmental sensors such as weather stations that we already had existing deployed at the system. This is one from an experiment we did in Hobart a fair while ago, but it looks similar to that. Other systems we set up is edge gateways. So this is one that we set up in Lansdowne. In Lansdowne up in Townsville, but it was similar. It was a similar type setup that we set up in Armidale here. And these devices have Bluetooth, LoRaWAN, and a 3G, 4G backhaul mechanism. So the Bluetooth is for that short range comms. So you typically set these up near high traffic areas such as pens, holding yards, stuff like this. And therefore you're able to then download data from multiple different ear tags or asset tracking tags, but also be able to then act as a gateway as well for those longer range comms for other devices out in the fields, and then ultimately backhaul it via 3 or 4G connections. So how do these devices talk to one another? So as I was saying, we use a different communications link, but typically we use the whole concept of using Bluetooth to be able to talk between multiple different devices. So for instance, we have this cow here being able to cow 5 over here, and they're able to exchange data and pieces of information about one another. This allows us to be able to then do a lot of this work around the data provenance and trust generation, as well as enable capturing for automated compliance certification. So not only is this device acting as a beacon to identify that cow, but it's also running some embedded logic internally to work out what that cow is doing. How often has it been drinking? How often has it been moving around? Stuff like this. So we run feature classifiers on the actual ear tags themselves. Some other presenters and some other have been talking about this. And ultimately, they talk via they can either talk via satellite comms, which is low data rate. So you typically will only get a packet once every 2 hours or so, versus being able to talk Bluetooth, you're able to exchange a lot more data by that mechanism. And then ultimately these relay nodes allow you to ship data off to gateways and stuff like that to get data to the cloud. So for our simulation, we're really focusing around these embedded devices that are exchanging data on the farm, because ultimately the rest of these systems all leverage what actual data is being generated on the farm. So we really want to be able to leverage that and be able to test those upper level systems with data that's representative of what an actual farm would generate. Now, the reason this work came about was because of COVID-19. We were able to get one experiment in just before Australia basically locked itself down at the start of the pandemic. So that was February, March. And then we were aiming to do some more experiments, and hopefully COVID settled down after May, June, but that never eventuated. So therefore we had to come up with a way to be able to then allow us to continue our work, and then therefore the simulator was born. So how do we test these larger IoT systems? So for instance, one way you can do it is through lab testing. So this is excellent for simple situations and cheap to perform. Easy to fix and troubleshoot issues that arise. So great for R&D applications and stuff like this, but it's hard to test those complicated interactions of those cattle and interacting with assets and being able to do classification. Another option is field trials, good for testing complex interactions. So being able to test those unique special cases where cows come in range with one another rarely, or do certain behaviours that are tricky. However, they're quite expensive to run. So both in terms of time and money. So you need staff and you need resources, and you need to set up dates and all that sort of stuff to be able to actually perform these experiments. Plus, they're also hard to troubleshoot and fix problems. So if you discover any problems with any devices, you've either got to round all the cattle back up to be able to use, or you run around a paddock and update those devices. So this is where simulation comes in. So we test that to any level of complexity in devices. Ultimately, it's all about the effort you put into developing the simulator, and the models gives you the results you want to put out. So, but ultimately, because it's software, you can then leverage that work in future iterations. Easier to cheap and run and iterate. So as I was saying, you basically are able to run this indefinitely almost. All it costs is some computation time and some power to just crunch the numbers on your computer. What we can also leverage is this ability to replay existing data sets. So both real and simulated. So for instance, from that first trial, we captured a lot of accelerometer data, a lot of positional data from both the series tag, plus also we had some cattle tracking collars. And we've got a lot of data from other previous experiments that were run for many other different projects. We're able to then leverage that data for troubleshooting. Plus we can also then pipe it into a simulator to be able to then generate new data. So for instance, if we have location data or geospatial data on an animal and a herd of animals, we're able to then cross-validate and go, hey, would this animal typically talk by Bluetooth to this other animal? Yes, no, sort of stuff like this, and what that RSSI potentially could have been, and what data then could be exchanged. As I said before, it's not affected by global pandemics, so it doesn't require anyone to leave their office or home to be able to do this sort of work. So it's great for the cases where access to farmers is highly limited. But it's also, but one of the difficulties of doing this type of simulation is hard to generate that realistic animal behavior and movement data. So being able to take what the animal typically does in terms of what its needs, desires, and wants are, and then turn that into code for a digital animal to be able to actually perform. So let's talk about a complex interaction in this case. So we have two cows. Cow 1 is drinking at a water trough here. Cow 2 is out here grazing. These circles here represent ranges of different devices. So for instance, the water trough has an asset tag. Cow 1 here has a smart ear tag, as well as cow 2. All these are talking via Bluetooth. So what's happening here is cow drinking is drinking from a water trough. So typically a lot of people are currently using this, just typical range to be able to determine if a cow was actually drinking from a water trough. However, one piece of work we've been working on is the ability for that ear tag to be able to classify the actions of the animal. So being able to then run the embedded logic on the device to go, am I drinking or am I grazing next to the water trough? Because there is a significant difference there from an animal ethics and welfare point of view. Is the cow actually drinking, or are they just grazing? And is that water trough dry and then just grazing next to it? So therefore, what we're able to do is effectively do this stuff where we're able to read the accelerometer, perform that activity classification, scan for other devices, and see, oh, I'm near a water trough, and I've also classified that I'm drinking. Therefore, my state should be drinking. Else, if I say I'm drinking but I'm nowhere near a water trough, then I'm technically unknown. I can't validate that I'm actually drinking, right? So therefore, we basically then broadcast that state that we either are drinking or not. Now, what we're also able to do is have a second cow, for instance, out here in the field grazing near it. For instance, you can have multiple cows around this also grazing and doing other activities. But what we were also able to do was go, all right, for each of the devices standing out in the field from cow, this is cow 2's logic, for each of the cows that say it's drinking, if I also see a water trough, then I should really trust that event, right? I can go, yes, I can validate that cow 1 is drinking from a water trough. Yes, I can see that the water trough is in range. Therefore, that snippet of information is actually useful for generating a piece of trust to say that that cow is actually then drinking and not just misclassifying, for instance, or doing something. So therefore, you can really start building higher levels of trust in your data, because it's no point in just saying a cow just recording everything it's doing, but there's no way of that cross-validating that data, because ultimately a cow can say whatever it wants, but it doesn't necessarily mean that cow is actually doing what it says it was doing. So in the simulator, how this looks like is we've effectively got this digital model of a cow. So we've got this simulated cow, which ultimately is herding dynamics, as well as hearing from other sensor data. This then feeds into an embedded application, which is effectively the same app that runs on our ear tag, and it does our sort of application logic. It does that logic of going, am I near a water trough? Am I also grazing, for instance, during the behavior classifiers, for instance. So we're able to pipe in the accelerometer data from a simulated cow, for instance, to do those behavior classifications. As well as that, we do all the communications logic, so work out encryption mechanisms and test all those sorts of mechanisms and stuff as well. How this all pieces
Carl,
together.
just giving you your 1 minute warning. Thanks.
Yep. So we have, so for instance, we can have multiple different entities. So this here doesn't necessarily have to be a cow with a smart ear tag. This can be a water trough that doesn't move and has no concept of movement. But it ultimately is still beaconing out information about itself. So you might have water level, for instance, within a water trough and want to test all those sorts of mechanisms. So therefore, we're able to model different entities and how they all interact with each other. Ultimately, it feeds into a server, which holds the entity state as well as world state, and performs the actual engine and works out, all right, when this cow wants to move to X, Y, Z in the field, it allows that and facilitates that to happen, and ultimately it feeds and stores all the data for us. We're a world of simulated, so the advantage of simulation is obviously it doesn't require any ethics. So it's ideal, as I said, the treating cows badly. There is no ethics considerations within simulation. Ultimately, there will be some cases where ethics is still required, especially if you're using human data or real world people data. However, if you're just purely doing simulations, there's no ethics required. So you can effectively test a lot of these edge cases where what happens if we leave a cow out in a field for 3 days without water? Does the system detect that? Or is it able to detect a herd of cattle that are starving? Stuff like this. So that's one way. Access to animal handlers are required to set up the experiment. So there's no handlers at all. Expensive and hard to scale. So let's say you do an experiment on 10 cattle, but then your next experiment, you want to do 50 cattle. You then require to find 40 more cattle, put all your devices on them, source the hardware and stuff. We can just spawn in 40 more cattle into our experiment and test what would happen. You require hardware, obviously, to collect data and make sure it's working properly and tested and stuff like this, even before you go to experiment, to make sure the data you're collecting is accurate and representative. With simulation, no hardware required. You still need some code around the embedded logic and stuff you want to test, but ultimately you're not reliant on finding hardware and sourcing that. Experiments have to be designed to ensure the welfare of animal. So as I was saying before, you can't really leave an animal out in a field for 3 days without water. That's cruel to the animal. It's unnecessary for the welfare of the animal to be able to do that experiment. But we don't need to worry about those welfare considerations when designing some of the more complicated experiments to test some of the real big edge cases or test some of the big logic questions we have in regards to being able to take welfare. As well as this, you can lose data through hardware failure and stuff like this as well. So this is where this point comes in. So, for instance, an animal might crack or break an ear tag or break a collar. You can almost lose all the data from that animal for the entire experiment duration. Where simulation, you get all the data no matter what. So, further research areas, we're aiming to develop more realistic animal models for cattle. So, behavior transition, activity-based time of day, feed intake, as well as flight mechanics from predators. So, being able to model that, implement RF propagation algorithms based upon real-world data. So, being able to better articulate, rather than just drawing a blank circle on a map and going, this is what a range of a typical Bluetooth device, really thinking about the environment, especially when you mix in trees and buildings and stuff like this. How does the RF propagate around that world? And then ultimately out in 3D world support. So we currently only are really simulating in a 2D plane. R&D applications, research provenance, trust compliance, testing validation of algorithms, so simulate novel logic. So this all sort of falls into one big picture. You're able to then do a lot of that research on desk research, basically fairly cheaply and easily, before you even have to go to a farm and engage in animal field trials. Validate your end-to-end systems for scalability. So, for instance, what happens if you generate 1,000 cows that are all streaming data at 2 hertz into a gateway? What does that look like? Does that gateway software start falling over? Ultimately, commercial applications could be testing device and density mixes of networks. So, for instance, you could have a mixture of different smart devices in your farm. So you might only have the stereo smart ear tags, for instance, but you might also have other assets that are other devices which are interacting with that, providing data and exchanging data. You're able to evaluate new algorithms for devices before you deploy them on actual hardware. So therefore, you can evaluate what is that logic or something going to be able to do and generate before you even engage in that rollout. Replay existing data to determine causes of breach events. So being able to look at previous data you've captured and going, why did that breach happen, or where could it eventually happen? For instance, you can go, all right, let's look at this, deploy some water troughs out. We know the cows migrate. Typically, ideally, you want to have a water trough less than 4K apart. Is what research shows. So therefore, you want to be able to protect possible breach events. All right. Any questions?
Thanks, Carl. We've got one question. I think you've started to cover it off in the final slides around the impact of other conditions, so effects of weather or grass distribution. Are they captured in the simulation at the moment, or is that something for future work?
That is definitely for future work. So currently, the cattle we're simulating have very dumb behavior mechanics. They switch between grazing. They know that we're typically modeling animals as grazing, but ultimately in future work, because you know, and it's run in real time, you're able to simulate how much the cattle has eaten during the day and be able to model then also down to the meter by meter level biomass density, for instance. So therefore, you're able to then go, all right, I know the biomass of this area. I know how much typically a cow ingests a day. Therefore, I can propagate that across the field. So there's definitely future work, and definitely something we're actively thinking of implementing. It's just all about time.